Morning. My name is Ray Ohl, again from NASA Goddard Space Flight Center, and I'm going to talk about Beyond Hubble, building the next generation space telescope. I'll focus on the science and technology for this new NASA mission. I'm building a prototype spectrograph for NGST, and at the end of the talk I'll focus on some of this technology work going on at Marshall and at Goddard Space Flight Center. It's important to realize that this is a huge project. Hundreds of people across the country at contractors and at NASA centers are involved. And my point here today is to give an overview of the program, to talk about all of their work in sort of a top-level fashion and compare it to Hubble, which was the last big optical near-infrared telescope that NASA worked on about 20 to 30 years ago. I'll start off by talking about Hubble Space Telescope, what its design was like, what kind of science it performed, and what its pluses and minuses are from a science point of view. I'll talk a little bit about the requirements of Hubble, the science requirements. The Next Generation Space Telescope, I'll abbreviate it NGST, I'll talk about the science motivation, how it differs from the Hubble Space Telescope, and the challenges to your community and other technology communities. So Hubble Space Telescope, at the top here you see a cartoon schematic of Hubble. The source, of course, is essentially at infinity. Collimated light enters the aperture, 2.4 meter diameter aperture approximately. There's a primary mirror, which is close to a parabola, which sends the light to a convex secondary mirror, which focuses it behind the telescope in the standard RC telescope fashion. It's an F-24 system. And the primary mirror here is a monolithic, room temperature. It's an egg crate type design, and has an areal density of approximately 180 kilograms per square meter. It's important to keep this in mind. It was launched in 1990, and again, designed in the 70s and 80s. There were a lot of upgrades and technology changes to the instruments over the course of the late 80s in preparation for this later launch. It was delayed because of Challenger. And of course, a big thing about Hubble is that it's in low Earth orbit and designed from the get-go to be serviceable. Every 2 or 3 years, there's a servicing mission, as I'm sure you know, with the space shuttle to replace some instruments back here and some other components on Hubble, which were thought to be possibly at risk. The wavelength range of Hubble is pretty outstanding. It goes from the far UV to the near infrared. This is associated with the mag fluoride coating cutoff of the optics, and thus is capable of doing a lot of amazing science. It's really hard to do any kind of justice to the science impact that Hubble has had. It's every grad student that you run into in astronomy these days, their thesis is somehow impacted by Hubble observations. Almost every field in astronomy has been significantly added to by this mission. So I'm not going to even try to do justice, but I want to compare it to what preceded it, so large ground-based telescopes. So on the left here you see a typical image of a couple of star-forming galaxies that happen to be orbiting each other, gravitationally bound. These are systems with of order 10 to the 10 plus or minus a couple of orders of magnitude stars. They're star-forming spiral-type galaxies. And this is a typical ground-based image taken from an NOAO telescope. Ground-based observatories, they suffer in the, as you get toward shorter wavelengths and toward, like the near UV and the near infrared, they suffer from significant atmospheric absorption. So that's, of course, one obvious feature about going into the advantage for going into orbit for Hubble is to have good performance toward the far UV and the near infrared. On the ground, you're also limited in resolution, spatial resolution on the sky. For most observatories, you're limited to about an arc second or half an arc second on good nights or with special equipment. So this is essentially a limit to the size of the point spread function due to atmospheric seeing effects. Stars twinkle, right? But when you go into orbit, you don't have to worry about this problem. You have other point spread function issues, of course. But the Hubble Space Telescope, after the corrective mission, performs at about a factor of 5 or 10 better than the typical ground-based observatory. So with a smaller field of view, of course. This is a typical image, this is a blow-up of M82, the central region of this edge-on spiral-type galaxy. So the stars appear to be a lot smaller. All right, so the punchline with NGST is that we want to see deeper into space. In a given amount of integration time, we want to see fainter objects and thus older objects. So this slide pretty much sums it all up. I could end it all right now if you like. On the left, this is an image called the Hubble Deep Field North. Basically, Hubble, with its wide field planetary camera and other instruments, stared at a patch of sky in the northern hemisphere. They did this for the southern too, but for 10 days. And they co-added the data. So this is a very deep image. This happens to be a star in our galaxy, but all these other points in here are all galaxies. If you ever get a better, you should see, some kind of a nice quality print of this. It's amazing. You can really see a lot of galaxies. You get kind of a feeling of the depth of space. This is a 30 arc-second by 30 arc-second image of the sky. And this is an image taken in the visible, so sort of in the blue to red regime. This is a simulated image for a computer model of NGST, showing the difference in signal to noise, essentially, for an exposure of the same duration. So for the same exposure time, NGST, because of its larger aperture, will be able to see deeper into space. These are two artist conceptions about of the NGST observatory. Right now, we're in a procurement phase. There are two vendors are preparing bids. One is a consortium of TRW and Ball, the other is Lockheed Martin. To give you a sense of scale, these sun shields here are about the size of a football field. I'll get more into the design later on, but this is what NGST looks like. Very open architecture, large, deployable, segmented mirror for the primary mirror. It has to be deployable because we don't have a launch vehicle with a shroud big enough for a 6 or 8 meter diameter mirror. Number one, we need a larger mirror to see these fainter, thus older targets. And it's optimized, the optical design is optimized for Hubble type resolution at 2 microns. The initial yardstick was for an 8 meter diameter mirror, but cost constraints have recently led us to revise this to a 6 meter diameter system. And that's what the bids will come in for. So these slides will be a bit confused. Sometimes you'll see 8, but keep in mind that 6 meters is what we're aiming at here. The wavelength range is between 0.6, so the red, to 10 to 20 microns. The system, again, has to perform in the infrared regime. So there's some important mission drivers here. Number one, the system has to be cool because you want to avoid black body radiation from the optics themselves, from the observatory themselves. So it has to be. So we're going to passively cool NGST using the sunshade to about 50 Kelvin. Number two, NGST will be stationed at the L2 point. So in order to limit background radiation from stray light and warming due to the Sun-Earth system. This is a much more thermally stable orbit. With Hubble and other instruments that are in Earth orbit, they're moving quickly around the Earth. They're seeing the sun, they're seeing the bright Earth, they're seeing the shadow Earth, they're seeing the moon. This is a very thermally unstable environment that you have to take into account. This makes things simpler for NGST to put them out there, to put the instrument out there. But of course, this means that we can't service it. This is millions of kilometers away. The primary mirror here will have to be some kind of flower petal type deployment from the central structure because it has to fit inside of this little shroud. And one of the key things to remember about design philosophy changes between NGST and HST is this forward-looking mirror design that in the future NASA wants to be able to build even larger apertures. All right, if you compare NGST to ground-based observatories, this is really the advantage of NGST. You can see this plot is on the left a log scale of the exposure time needed to perform a certain type of astronomical observation, some kind of survey, it doesn't matter. On the bottom axis here, on the x-axis, this is just the wavelength in the near infrared. So typical large 8 meter 10-meter class ground-based telescopes follow this kind of a curve on this plot. So the higher the curve, the better, basically, on this plot. The lower the exposure time needed to do a certain type of observation. This curve essentially, well, you can see these dips in here due to the atmospheric absorption features in the near infrared, and ground-based telescopes peter out when you get over here to longer wavelengths. HST does better. It doesn't suffer from that kind of atmospheric attenuation. There are plans for even larger telescopes. Of course, they'll suffer from the same kinds of problems. NGST, at least with an 8-meter diameter aperture, is up here somewhere, around 1 on this plot. So you can see the advantage of going to space with such a large aperture. And certainly it's superior to HST and to ground-based telescopes for mid-infrared wavelengths. So the key is better sensitivity and tighter and more stable point spread function. The ground will still be good for high-resolution spectroscopy and very large field of view applications. So as I said before, the main thing about NGST is viewing the time when galaxies were very young and stars were just forming up. This is kind of a cartoon illustrating that. This is a Kobe map of the cosmic microwave background radiation. These red points in here are thought to be, well, they're brighter areas of the cosmic microwave background radiation. They're thought to be areas where material in the early universe, just after the surface of last scattering, after the Big Bang, when photons ran free from the hot mix of matter and light. These are thought to be denser areas. And it's thought that these denser areas gravitationally coalesce to form clusters of galaxies and galaxies. So we're trying to image the universe at this time. When these stars and galaxies first turn on, you get a lot of hot UV light of optical emission that's then redshifted into the near and mid-infrared. In order to do this, to see that far, we need to be zodiacal emission limited. We need to be, NGST observations need to be dominated in terms of background only by the scattered light and emission associated with dust in the plane of our solar system. So we thus put it at the L2 point to avoid interference from the sun and the Earth, and we make it cryogenic. Again, this puts NGST in some context with other NASA missions. On this plot, you see time here from left to right, or redshift. This is a measure of the expansion of the universe, the fractional expansion of the universe, or the shifting of the light into the red. Kobe imaged the universe over here at sort of the surface of last scattering, millions of years after the Big Bang. HST images the near universe. So if the universe is about 10 or 15 billion years old, it images things back to about, well, 5 to 10 billion years ago or so. That's the Hubble Deep Field on this plot. NGST will cover this whole range out to about the position of this red line. So this is where some astronomers think that the early galaxies just started to form up about that time. The baseline design cartoon is like this. There's a large 6-meter diameter mirror with folded up petals that can fold up and deploy, a secondary mirror on a stalk, which is another precision deployable structure. We call this the optical telescope assembly. Behind all of this is a box containing the science instruments. We call it the science instrument module. And connecting this structure to the support module is an isolation truss. The support module is warm. It will contain all the housekeeping needs of NGST. And so everything that's warm is sort of on the right-hand side of the sun shield here. The baseline optical design is as follows. It's a 3-mirror anastigmat, which means it's corrected for third-order aberrations. It starts off with a large 6-meter diameter, nearly parabolic primary mirror, a hyperbolic secondary mirror, which creates this Cassegrain focus, but the images are not optimized. Nothing really happens with this Cassegrain focus. But you can sort of look at it as there's a tertiary mirror here, a third mirror, a prolate ellipse, which re-images that focal plane to another point nominally over here somewhere, but there's a fold mirror which sends the light back behind the telescope to the science instruments. This fold mirror exists at a pupil. It has 2 functions in the yardstick design. Number 1, it can be used to help guide NGST. So it can be put on actuators. This is up to the vendor as to whether or not they need to do this. But we can relax requirements on NGST's guidance system by having this mirror, which can use a feedback from one of the science instruments or a guidance camera to correct for pointing problems. The other thing is that because it's at a pupil, if you put actuators on this mirror that can deform the mirror, then you may be able to do some wavefront correction. It's not planned, however, that this would be an active wavefront correction. If the vendor wants to do that, it'll probably be something where they'll detect a sag in the system, some kind of aberration, do a correction, that'll last for an observation or 2 or 3, and then at some other point reassess the wavefront and go on. This is not something that'll be correcting while the observations are in progress. The other thing you'll notice about that design is that it's an open type architecture. It's a stray light nightmare, and so there'll be a lot of baffling issues back here. The telescope and instruments will be cryogenic. Another major difference, NASA has flown cryogenic missions before, sort of, for example, NICMOS on HST, but of course that's a terrible requirement to combine with some of these other features. ESA has also flown some cryogenic missions. It'll be at the L2 point, so it has to work once, and that's it. That's a heavy-duty requirement from NASA, is that we can't fail, it has to work once. There's a fast steering mirror, which may alleviate some of the requirements on guidance and control. And a major philosophy difference is that we have this forward-looking design. I spoke about the instruments, the instrument complement on NGST, and this is a list. The instrument that probably you'll see the most interesting images from in the press is called the near-infrared camera. This is sort of equivalent to Hubble's wide-field planetary camera. Of course, it'll operate, however, in the near-infrared, and the US is responsible for that instrument. The other additional feature that this instrument has to perform, in addition to taking science exposures, is to be able to use, to provide the ground with wavefront sensing and control data. So we take the detector on this camera and step it through focus and use these out-of-focus images, in-focus and out-of-focus images, with phase retrieval or phase diversity algorithms to find out what may be wrong with primary mirror alignment. The Europeans are providing this near-infrared multi-object spectrograph. The US may provide some important components to this instrument, but the point of this instrument is that in one exposure, with one pointing, you can obtain spectra of many different objects in the field, of order 100 objects in the field at one time. So this is a way of multiplying the effective observing time of this instrument. And most spectrographs on the ground, they take spectra of one object at a time. So if you multiply that by 100, you're multiplying observatory efficiency by 100. Use a large format detector for that. I'll show more slides about this in a bit. This is the instrument that I'm building a prototype for. My prototype will, in addition to testing some technology for NGST, will also be a facility instrument at Kitt Peak. And we're building another prototype that I'll also talk about at Goddard, which will also be a facility instrument at Apache Point. So there are a bunch of ground-based telescopes that will benefit from some of this technology work. The third instrument is a mid-infrared camera and spectrograph, kind of a low-resolution spectrograph. It's a collaboration between JPL and the Europeans. And the latest addition to the instrument complement is a fine guidance sensor that will provide guidance feedback, pointing feedback to the telescope. Again, the primary technology development challenges here are deployable, large, lightweight, cryogenic primary mirror segments with this low areal density. And that areal density includes these cryogenic actuators that have to perform positioning, mostly alignment. And of course, there's a big push toward understanding this wavefront sensing and control algorithms that we'll use in conjunction with actual science data to align this telescope on orbit. The last two bullets here mostly pertain to instrument development here. There's a significant amount of development in the US for large format, these near to mid-infrared detectors. I'm not going to talk at all about that. It's mostly an effort based for focused on the instruments. There is a significant amount of MEMS work as well for the multi-object spectrograph that the Europeans will build, but the Americans will provide a significant component to detectors and MEMS arrays, probably. It's not completely worked out yet. But this development's going on here at Goddard. This is essentially a programmable slit array. It uses MEMS technology to find the stars in the field that you're interested in. There are 3 vendors that are providing AMSD mirrors for NASA. This stands for, again, for Advanced Mirror System Demonstrators. And unfortunately, I can't say very much more than what I can show on these slides. Ball is one of the vendors. These mirrors are all about 1 meter across, and all of them meet the areal density requirement for NGST. The reaction structure here is graphite epoxy. There are these cryogenic actuators which go between the reaction structure and the mirror segment. It's a lightweighted geometry here, this case beryllium for Ball. The actuator plan is as follows. There's a central actuator which can control the mirror's radius, so that pushes on the substrate and pulls on the substrate to control its radius. There are other actuators that are on the outskirts here to control tip, tilt, and focus, and some backup actuators, 3 backup actuators. Another vendor is Kodak, working with a ULE blank, same type, same basic design, and BF Goodrich is the 3rd vendor. All these mirrors are in construction right now and will be tested in the near future at Marshall Space Flight Center. Image-based wavefront sensing and control. This is a simulation here. They've been doing a lot of computer work at JPL and at Goddard on simulating exactly how to align these mirror segments. This is a simulation here of the wavefront error associated with a misaligned NGST type system. This is the point spread function for that misaligned system. Looks like a mess. As you improve alignment using phase retrieval or phase diversity algorithms, the point spread function looks better, and once fine alignment is complete, there's a nice crisp point spread function here. Again, this is something that the near-infrared camera will provide the scientists and engineers for this alignment. We have a test bed at NASA Goddard which has 3 mirrors, and we're learning how to phase. We're testing out the algorithms on these 3 mirror systems. It's going very well. We're going to upgrade to multiple mirror systems until we have something that looks like this in the next couple of years. Multi-object spectroscopy. The multi-object spectrograph on NGST will operate as follows. There'll be an imaging mode, most likely, where you'll be able to take a picture like this. You can look at stars and galaxies. And then when you flip a switch, you see spectra, wherever you see a point here. That is, you have some kind of a programmable slit array for selecting the objects that you want to see a spectrum of on the left. So we have a 2D detector that'll detect many spectra at one time. The scientist will probably just do some kind of software mask to select the spectrum, the spectra that they're interested in. There are 2 prototype spectrographs being built at NASA Goddard to test this MEMS technology for performing this object selection. One is called IR-MOS and one is called RIV-MOS. It's an all-aluminum, sort of athermal type design with a lot of aspheric optics, re-image a telescope focal plane onto this micromirror array. Then the spectrograph cavity is back here. There's an interesting mirror here, which is a biconic mirror. It's a toroidal surface. All these optics here are diamond machined. This toroidal surface, the function is to correct for astigmatism in the aft-end optics. And the spectra or images are then collected on this detector back here. And this is a picture of the Kitt Peak 4-meter observatory. So the point here for NASA is to see how viable this micromirror array technology is, see if we can actually pull this off and get some science results using this technology, look at contrast ratios and things like that. And then, of course, there's a big benefit from Kitt Peak for having a facility instrument. This is what the micromirror arrays look like. We're just using a commercial unit for this instrument, although we have custom ones that are in fab for NGST at NASA Goddard. There's a big technology challenge here for this biconic. It's a toroidal surface, different radii of curvature and conic constants. It's also off-axis in 2 directions. It's quite a difficult surface to fabricate. But it allows to give us this, it gives us this compact design. And indeed, if we can pull off this fabrication with in diamond machining, we can, I think, give the designers a little more freedom for the real NGST instruments, which also have a lot of space constraints, which are very similar to the constraints we had for this ground-based telescope. It's difficult to fabricate, it's non-rotationally symmetric, and there are only a few capable institutions. We're working with 2 of them to try 2 different methods of diamond machining for fabricating this mirror. One is at NC State. Many of you saw this set up the other day. Tom Dow, Alex Sohn, and Ken Gerard are working on it. It's going quite well. This is some in-process data we have, still about a factor of 10 out of spec, but in the next month or so we should have it down in terms of figure, and the micro-roughness is already looking quite good. The other company or institution that we're working with is the Laboratory for Precision Machining at the University of Bremen. They're using a Precitech machine for raster fly cutting the part. This is a picture of it in action. They've gotten some good numbers on some test parts, which are spherical, but we expect some results from this biconic mirror within the next few weeks as well. Things are going quite well at both institutions. So I mentioned a lot of things. Give you a quick tour of the NGST mission. I mentioned a few technology efforts, the MEMS efforts associated and the detector efforts associated with the instrument development and the mirror technology development efforts underway to improve what we can do in terms of primary mirror segments, that is large, lightweight, deployable, active, cryogenic mirror segments. Wavefront control algorithms that are necessary for aligning these segments. And there's a lot going on in precision deployable structures. For example, that secondary mirror stock, but I just don't have time to cover everything. And what makes this mission very difficult is not so much that we haven't done these individual tasks, phasing segments or flying cryogenic missions, but that everything is gathered under one umbrella here. We have a lot of normally just very challenging technology requirements that are all pooled together for this mission, and we can't service it. There's no way we can bring it back down. And the technology development philosophy difference between this mission and the last big optical near-infrared telescope that they put up there is that we hope to use this technology for future instruments that'll be even bigger, future large aperture telescopes. That's it.